So let's start off with some sample diploma questions. A student has three identical spheres, K, L, and M, on insulated stands equally spaced in a line as shown below. The charges on the spheres are 3, -5, and +2. At point P, above sphere L, the direction of the electric field is mostly. So this one's a lot closer, and you have to remember that electric field is equal to KQ all over R squared. So because it's an inverse squared relationship, the further you are away, the weaker the field's going to be. So this one's the only one going to give it any significant field. So it says that sphere L is negative. So negatives go towards it. So it's going to be towards the bottom of the page. D. Which of the following graphs best shows the relationship between electrical field strength and distance? So if we want a straight line, we got to use that inverse squared relationship. And the electric field from a positive point charge of that is, okay. So we're going to use our E equals KQ all over R squared. We can find the magnitude, so 8.99 times 10 to the 9 newtons meters squared per coulomb squared. And then we have our charge, which is 5 times 10 to the -6 coulombs, all divided by our distance, 0.2 meters squared. So if we plug that into our calculator, let me just focus that and change the lighting. Yeah, whatever. It's fine. So alpha K times 5 times 10 to the -6 divided by 0.2 squared. So we get the magnitude to be 1.1 times 10 to the 6. Newtons per coulomb. And you have to remember that it's positive, right? So positives are always going to go away because Pedro is going to go away. So positive is always away, so it's away from the point charge. D is the correct answer. Okay, so let's start this voltage current uniform electric fields. This is a mishmash of a lot of stuff that didn't really fit anywhere else, so I put it all together in one big giant lesson. So curriculum things: compare qualitatively gravitational potential energy and electric potential energy. Define electric potential difference as a change in electric potential energy per unit charge. Calculate the electric potential difference between 2 points in a uniform electric field. Define electric current. Describe with numbers the motion of electric charge in a uniform electric field. Lots of stuff in this one. Explain with numbers electrical interactions using law of conservation of energy. Use accepted scientific convention like electron volts when appropriate. Analyze with numbers the motion of electric charge following a straight or curved path using Newton's laws, vector addition, and conservation of energy. So that's like projectile motion stuff. And use free body diagrams to describe forces acting on a charge in an electric field. So that's what we're going to do. So why is it difficult to figure out how a test charge will move in an electric field of a point charge? Well, let me answer that question for you. So the electric field here is different than the electric field here, than the electric field here, than the electric field here, right? As we move further away, our electric field is weaker, right? So if we think about it in terms of like acceleration and things like that, like F net equals, ma. As our electric field gets weaker, our acceleration will get weaker, and then we have this changing acceleration, which makes it super difficult to analyze. So it's because the field is changing. That's why it's so difficult. The field is changing. So what we need is we need something like gravity, right? If this is my ground here, and I drop a ball here, well, my field is 9.81 meters per second squared, right? And if my field here is 9.81, and if I'm over here, my field is 9.81. No matter where I am close to the surface of the Earth, it's a uniform 9.81. So that's what we want for electric field. So the way that we can create that is we can do this. So let me open up this. Just give it a sec. Let's put a grid on there. Perfect. So this is a new HTML5 version. I've never seen it. So if we, well, yeah, let's keep that electric field on there. All right, so you can see it always goes away from our positive charge. So I'm going to put another one here. 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 And let's put ones in between. Oops. There we go. And then we'll put negatives down here. There we go. And when we do that, right, when we look at the field between the charges here, well, it actually looks like it's pretty uniform. It's pretty straight, right? What can we do here? Oh, so the fogginess, like how clear it is what? Sorry, this is new for me. So what we get is we get a uniform field in here. We can put a little sensor here, right? No matter where we are, our sensor is downwards, right? No matter where we are in here, between these fields, we get this nice downward uniform field, which is kind of like, works like gravity in a way. So in a uniform electric field, the force exerted on an object will always be constant. So that's nice. We have constant force. We have constant acceleration. We can do that. And we can use this formula here where our electric field equals Fe over Q, where E is our electric field, Fe is our electrostatic force, and Q is our charge in our field, right? So if I just move Q up here, like that, you'll notice that, well, we had this formula last year that was Fg equals mg. Well, instead of Fg, we have Fe, and instead of a mass, we have a charge, and instead of a gravitational field, we have an electric field. So it's really the Fg equals mg of physics 30. It's the same idea. So how do we use this formula? Well, a question like this. So a good indication that we're using this is we have a uniform electric field here. So it says that it's to the east, so to determine the electric force acting on the charge. So I'm going to draw a little picture here. So it says that our field is to the east. So to get a uniform field, what you need is you need a positive plate and you need a negative plate. And they can go in any direction. But because Pedro would move from our positive plate to our negative plate, right? That north, east, southwest. That's how we get our field to be east. Oh, that's bright. Let me see if I can adjust the color just a smidge on that. Yeah, that's a little bit better. Ish. Okay, so that's how we go to the right. so it says that, so anywhere in this, the electric field is the same. So the electric field is 2.2 times 10 to the 4 newtons per coulomb anywhere in here. So we place this -8 microcoulomb charged object in the field, determine the force acting on it. So Fe equals EQ, right? That's usually how I write it out. I don't know why they write it the different way in the formula. So my electric field is 2.2 times 10 to the 4 newtons per coulomb. My charge is 8 microcoulombs, so times 10 to the -6 coulombs. Remember, don't put in positives and negatives for charge. We'll figure out direction after. So if I plug 2.2 times 10 to the 6 multiplied by 8 microcoulombs, so times 10 to the -6, I get a force of 17.6 newtons. Right? But force is a vector, so we need a direction. While my charge is negative, my negative is going to be attracted to that positive plate. So the answer for my direction is west. Okay, so let's do a board question. A proton enters a uniform electric field between two parallel plates in two situations. Label the plates as positive or negative. Draw in the arrows between the plates to represent the electric field. Okay, so pause the video, try it on your own, see if you can do it. So we have a proton, it increases in speed. So if it increases in speed, it's probably because it's attracted to the negative plate here. And it's going to speed up as it gets attracted to that negative plate. And my electric field is always the direction Pedro would go. So it's away from the positive towards the negative. Okay, try out this one. Electron decreases in speed. See if you can figure that out. Pause the video. So if it's decreasing in speed, it's probably because it's being repelled by the negative plate. Right? Pedro tells us it goes from positive to negative, so it's actually the exact same thing. There we go. So we're going to talk a little bit about potential energy. So what can I do to give a mass potential energy in a gravitational field, right? If we were out in space, in the middle of nowhere out in space, and I put an object just in the middle of space, well, it's just going to float there, right? So what I need is I need a gravitational field. So what provides a gravitational field? Mass, right? So this is Earth. It's our flat Earth, but just because it looks flat to us. So we have the Earth here, right? So we have this gravitational field towards the Earth. Okay. So what I can do is to give it potential energy, I need a mass. So I'll stick a mass in here, right? If I have a bigger mass, it's going to have more potential energy than a smaller mass. And if I place that further away from where it wants to be at the Earth, it's going to have more gravitational potential energy. So a bigger mass is going to have more potential energy, and if I place it further from where it wants to be, it's going to have more potential energy. Okay. Think of the same thing. So we need a uniform electric field. So let's have some positive plates up top and some negative plates down below. Right, and we can use a positive charge. So we have our field just like above. Well, how can I give it more potential energy? Well, I can put a charge in here, right? If I put a bigger charge in here, like something that's 2+, it's gonna want to go down more. And my positive charge wants to be by this negative plate. So if I place it further from where it wants to be, well, it's going to have more potential energy. Same idea. Gravitational potential energy and electric potential energy are very similar. So voltage is called electric potential difference. So electric potential difference is the change in electric potential energy per unit of charge. I don't like that definition, but sometimes questions show that definition in there, so you need to know this definition of electric potential energy. So we have two formulas for it. Sorry, electric potential difference, not energy, voltage. So we have two formulas. We have this formula here, electric field is equal to voltage over distance, and we also have voltage equals energy over charge. Okay. Something you need to notice is this is a field. This is energy, which are different. So I like to call this EPE, electric potential energy. So I will call it EPE, but on your formula sheet, this is how it's written, and you have to know which one is which. So this is an annoying term for voltage. Students don't understand it. What's the point of using that definition if students don't understand it? So I'm going to give you voltage in easy terms. So to increase the voltage of a system, you add more charge. Okay. So if I have positive side over here, I have negative side over here, this has a certain amount of voltage, right? So voltage doesn't do anything on its own. It gives a potential for something to happen, right? So if I have an electron here, right? That electron might want to leave this side and come over here, but it doesn't really want to that bad. But if I put more charge on this side, and I have more charge on this side, well, this electron doesn't like being here more because there's more negatives, it's being repelled more, it's being attracted here. So this has more voltage, right? So the potential for it to jump across is kind of like its voltage. That's the way that I like to think of it. So let's do an example. So calculate the electric field strength between two parallel plates that are 5 centimeters apart if the potential difference between the plates is 18 volts. Okay, let's draw a little picture of what's going on here. So we have two parallel plates. Like that. Okay, and then it says that they are 5 centimeters apart. And the potential difference between the plates is 18 volts. So we have our new formula where electric field is equal to voltage over distance. So this one is nice and easy. We can just use that one to figure it out. So we have 18 volts divided by 0.05 meters, and 18 divided by 0.05 is 360. And notice we were newtons per coulomb before with electric field, but that's the same thing as volts per meter. So we can use volts per meter as our answer. So that's our electric field. Now, the second part of this question says, calculate the electric field strength halfway between the charge plates. So if we're here and we're 2.5 centimeters away, how is that going to change? Well, if you're thinking, oh, it's probably going to be half or something like that, you are wrong, right? Because what did we say about the electric field between these plates? It's uniform. So here at 360, 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 everywhere between this plate is going to be 360 volts per meter. So what changes then? Well, if this is constant, then what changes is our voltage, right? So electric field times distance equals voltage. If I move that up there, well, if we go 360 volts per meter, and we multiply that by, now we're no, centimeters, 0.025 meters. Now we're only 2.5 centimeters. Well, what's going to change? I don't know why you need a calculator. So that's going to be 9, right? So that's important, 9 volts. So here, it's 18 volts. Here, it's 9 volts, right? 3/4 of the way, maybe you can do the math. Well, it's going to be, what is that, 13.5? And then here is 4.5. So different spots have these different voltages, right? But what stays constant is our electric field. So it's really important that you know that idea. So we can use conservation of energy with these plates. So when a charged particle is put in a uniform electric field, it begins to accelerate. If it's accelerating, it's gaining kinetic energy. Where is this kinetic energy coming from? Well, remember we have this electrical potential energy, EPE. We have this electrical potential energy. That's where it comes from. So just like gravitational potential energy, it's electrical potential energy. So determine the maximum speed an alpha particle obtains if it moves from rest across a potential difference of 250 volts. We can do that. So we have our positive plate, our negative plate. We have our alpha particle, which is the charge of 2+. So if it goes across these plates, it says that across the plates it's 250 volts. Well, we want to know, 250 volts. We want to know how much speed it's going to be. Well, here, right, it's where it doesn't want to be. It wants to get away from here. So it's got electrical potential energy. It's going to speed up, speed up, speed up right before it hits the plate. It's got kinetic energy. So we can use physics principle number 5. Our energy before equals our energy after. And before we have electrical potential energy. After we have kinetic energy. This is one of our new formulas, which is voltage times Q. I put bars on top of our voltage because when we break this down into 1/2 mv squared, we have velocity. So I want to make sure I differentiate between the two of them. Okay, nothing cancels out. We want to find speed. So we can move our 2 up top. We can move our mass down below. And we can square root it, and we can find V. Okay? Or V is in velocity. So 2 times 250 volts times our charge of our alpha particle. So an alpha particle is 2 times the elementary charge. So 2 times 1.6 times 10 to the negative 19 coulombs. Its mass is on the back of our data book, right? So you have it here, and it says that it's 6.65 times 10 to the negative 27 kilograms. Okay, and we have to not forget to square root that. Actually, I'll use my on-screen calculator for this bigger one. 2 times 250 times 2 times 1.6 times 10 to the negative 19. Divide that by 6.65 times 10 to the negative 27. We get that. This is faster than the speed of light, which isn't possible, so that should indicate, oh, we did something wrong. We forgot to square root it. So we square root it, and we get 1.55 times 10 to the 345 meters per second is our speed of our alpha particle as it goes across that voltage. Okay. So let's do a board question. Give her a pause, figure it out, see what you can do. So determine the voltage required to stop a 6.5 times 10 to the 6 meters per second electron when traveling in a uniform electric field between parallel plates. Okay, I will do it. Make sure you try it first. So we have, it's an electron, right? So if you're trying to stop an electron, right, it would slow down, slow down, slow down, slow down, stop going that way, right? Here it has a lot of kinetic energy. And here it's where it doesn't want to be. So if it's where it doesn't want to be, then it's got a lot of potential energy, right? So this is just the same thing as before. Physics principle number 5, where our EK now is turning into EPE. This is 1/2 mv squared. This is VQ, like that. And we're trying to find the voltage. So all we have to do, just gonna put the 2 down there. All that we have to do is move the voltage, sorry, the charge over there. So it's an electron, which is 9.11 times 10 to the negative 31 kilograms. It tells us the speed, 6.5 times 10 to the 6 meters per second squared. Charge of an electron is the elementary charge. And then the 1/2, the 2's got to stay down there. So if we plug all that in to our calculator, make sure to square that speed. We divide it by 1.6 times 10 to the negative 19. Then we end up getting E equals 120 volts. There we go. That's how you do it. Hopefully you got that right. So now we need to talk about something which is a little bit weird, which is the electron volt. So it's used in modern physics. We're going to use it a lot in our last unit, and you're going to love it. But when we use it right now, you're going to kind of hate it. So we got to get used to it. So it's the amount of energy gained by an electron as it passes through a potential difference of 1 volt. So let me explain what that means. So if I have an electron, and we have a voltage of 1 volt between these. And if I put my electron here, and it goes to there, it's gone across 1 volt of voltage, right? So here it's got electrical potential energy. Here it's got kinetic energy because it speeds up. So my EPE is going to equal my EK, and VQ is going to be equal to EK. So my voltage is 1 volt, and my charge is 1.6 times 10 to the negative 19 coulombs, because that's my electron, and that's going to be my kinetic energy. So it's 1.6 times 10 to the negative 19 joules is my kinetic energy, right? This is the amount of energy that an electron will gain as it goes through 1 volt. This is an ugly number. So instead of saying, well, 1.6 times 10 to the negative 19 joules, what they said, that just equals a thing called an electron volt. Kind of like, well, 12 beers, that's weird. Let's call it a dozen and put it in a pack together, right? Only this is really small, so we call it 1 electron volt. So that's our kinetic energy. So an electron will gain 1 electron volt of kinetic energy for every volt that it passes through. And like I showed there, an electron volt is just 1.6 times 10 to the negative 19 joules. Okay. You have this in your data book. So in your data book, you have this conversion. An electron volt is equal to 1.6 times 10 to the negative 19 joules. So you have that. It's just a conversion factor. A little tidbit, which won't make sense now, but when we do a question, it will make sense. So if your energy is in electron volts, you don't need to divide by Q to find your voltage. I will explain what that means when we do the next example. So an electron is traveling with a kinetic energy of 30 electron volts. It enters through a hole in a positive plate. It slows down as it travels to the positive plate. Sorry, it slows down as it travels from the positive plate to the negative plate. It has a kinetic energy of 20 electron volts when it collides with the negative plate. Determine the electrical potential difference between the charged plates. Okay, so we're going to do this the hard way, and then I'm going to show you a much more easier way of doing this. So an electron is traveling. It slows down as it travels from the positive plate to the negative plate. So we have our positive plate. We have our negative plate. We have our electron. You go through. Here it has kinetic energy. So a way to measure kinetic energy is in electron volts. It's got 30 electron volts of energy, right? Here, it also has kinetic energy. It has 20 electron volts of kinetic energy, but it's also got electrical potential energy because that electron isn't where it wants to be. If I hold that electron there, it's going to shoot off the other way. So it's got both of those. So one way you can do this question is you can say, I hate electron volts. I want to switch everything to joules because electron volts and joules are the same thing. So you can do that. So you can go 30 electron volts. And the back of our data booklet tells us 1 electron volt equals 1.6 times 10 to the negative 19 joules. You can also go 20 electron volts, and 1 electron volt equals 1.6 times 10 to the negative 19 joules. Those cancel out, and you can calculate those, which we will. So it's just 30 times 1.6 times 10 to the negative 19, and then 20 times 1.6 times 10 to the negative 19. I see my mistake there. Fix that. Good. So here it has 4.8 times 10 to the negative 18 joules of kinetic energy. And then here it has 3.2 times 10 to the negative 18 joules of kinetic energy. Lovely. So now we use physics principle number 5. And we say that our energy before is equal to our energy after. So before we just had kinetic energy. Oops. And then after we have kinetic and electrical potential energy. Okay. We know these in terms of joules, so we don't have to break them down. And what are we trying to do? We're trying to find the electrical potential difference between the plates. So we're trying to find voltage. So I'll move this to the other side. So I'll minus an EK after. So EK before minus EK after is equal to EPE. And then this is equal to VQ. So then I would divide by Q. And I could find my voltage. Right? So we end up getting my EK before is I don't want to go too low, 4.8 times 10 to the negative 18 joules. That's what we found there. It's there. Minus my EK after, 3.2 times 10 to the negative 18 joules. We divide it by Q, charge of the electron. And we can find our voltage. So when we do that in our calculator, right, we take this minus this, and we divide it by 1.6 times 10 to the negative 19, and we get, 10. 10. But there's a much easier way to do that, right? We had 30 electron volts here. We have 20 electron volts here. An electron's going to gain 1 electron volt of kinetic energy for every 1 volt to go through. So it's kind of going the opposite way here, so it loses 1 for every 1 volt to go through. So it makes sense that between these two plates is 10 volts, right? And what we did is here we took 30 times 1.6 20 times 1.6. And then we took those answers and we divided by 1.6. So we're timesing it, dividing it by 1.6. So it doesn't make sense to do all that work. So it's just going to be 10. You just 30 minus 20. What you end up finding, so if we go back to this right here, if this is in electron volts, then we can just get rid of this, right? So I can just go 30 electron volts minus 20 electron volts, and that'll get my voltage, which is 10 volts. So we just don't divide it by Q if we are in electron volts. That's all. Yeah. So something we need to talk about is current. So current is the amount of charge passing a reference point per unit of time. Current is measured in amperes, or if you're cool, amps. It's also known as a flow of electrons. So for you to have electrons moving, you need a potential difference. You need a voltage to cause a current. So this is our formula for current. Current equals charge over time. So current can be coulombs per second, which is an amp. Charge is in coulombs, times is in seconds. There should be a small t right here. So I have a little analogy for you because I'm throwing a lot of stuff your way this lesson. This is an intense lesson. So to toboggan, what do you need? Well, you need a toboggan, you need a person. But what makes tobogganing fun is you need a hill, right? Without a hill, it's not very much fun. So you need a hill, which is a difference in height, which is kind of like a potential difference. It's kind of like a voltage. So when you're trying to like sort all these definitions they give you in your brain, think of voltage as kind of like a hill, right? A person's kind of like an electron, right? And say you go to the hill and your little brother tags along, but you want to toboggan with your friends and you want to hang out with your little brother. So you give your little brother a task. You're like, you know what, little bro? What I want you to do, he's kind of nerdy. What I want you to do is I want you to count how many people go down the toboggan hill every second. And what he'd be measuring is he'd be measuring current, right? If you count how many electrons people pass a point in a period of time, you have your current. So the hill is voltage. The number of people that pass a point in a certain amount of time is your current, and the person is the electron. Okay? So how many electrons pass a point in 1 second in a conducting wire when 1 ampere is flowing? So these are the types of current questions that you can have. So what you need to know to do these questions is you know that 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. Okay? That's what you need to know. And you need to know your formula, current equals charge per time. So what they give us is they give us our current in this question. They give us our time, so we can figure out a charge. So we just move that up top there. So our time is 1 second. Our current is 1 amp, symbolized with an A. So our charge is 1 coulomb. Well, that's really easy. But it's asking for how many electrons pass a point. So now what we need to do to finish it off is we need to use this. We know that we want to turn coulombs into electron, and we know that 1.6 times 10 to the negative 19 coulombs is equal to 1 electron. We'll cancel that out. So we just have to go it's 1 times 1 divided by 1.6 times 10 to the negative 19. So it ends up being a lot of electrons. It ends up being 6.25 times 10 to the 18 electrons. Okay. So what I would like you to do is I would like you to try it. Try it, pause it, see how it goes. Each minute, careful, your units. So I will go through it here. says how much current in amperes are flowing if 1.5 times 10 to the 19 electrons pass a point in a conducting wire each minute. So we need I equals Q over T. To figure out how much current, we need a time. Well, this is easy. That's 60 seconds. That's 1 minute. They tell us it's got to be in seconds. But we need to figure out this. So we can figure out that with electrons because they tell us we have 1.5 times 10 to the 19 electrons. Cancel out electrons with coulombs. One electron has a charge of the elementary charge, 19 coulombs. Electrons cancel out. So to figure out how many coulombs I would get from 1.5 times 10 to the 19, I just have to go 1.5 times 10 to the 19 times 1.6 times 10 to the negative 19. And I end up getting 2.4 coulombs. Now I'm ready to finish this off. This is 2.4 coulombs divided by 60. So my current is 0.040. I have 2 sig digs in the question, add that 0 there. Amps is my answer. Okay, hopefully that went okay. So the last thing that we're doing today is we're going to do projectile motion style questions, but instead of them being in a gravitational field, they are in an electric field. So when a charged particle is given a horizontal velocity as it moves through charged plates, it becomes a projectile motion question. So the only difference is electric force pulls at the charged particle, not gravity. So let's see an example here. So an electron is moving horizontally at a constant speed of 3 meters per second when it enters the 1.5 Newton per Coulomb electric field. So draw a free body diagram of the forces acting on the electron. So because it's an electron and it's a very, very small subatomic particle, right? Gravity isn't very significant in it. So when it goes across these plates, electron, it seems to get pulled down. So the only force acting on it when it's between the plates, let me just switch to this. It's so much easier to do this. So we have our plates. It gets pulled down like that. So the force acting on our electron is it's going to be an electric force that's downwards, right? Gravity is so small that we don't need to include it in our free body diagram. So we want to determine the vertical displacement of the electron as it travels across the plates. So it tells us that this is 16 centimeters. And that's pretty much it. Okay. So we can write an F-net equation for this. So if we don't need gravity in there because gravity is too small, we can say that F-net equals Fe. This is mass times acceleration, and this is our electric field times our charge. Right, so we can figure out information about that, but we want to determine the vertical displacement of the electron as it travels through the plates. So we want to find out, what's that? That's what we're trying to figure out. So firstly, it's an electron, right? So if it gets down, our positive plate's going to be up there, our negative plate's up there. Let's add that onto that, so that's nice. But we can treat this like, I'm just going to leave this for here right now. We can treat this like a projectile motion question where we have x. Let me just move that up a little bit. Where we have our x and we have our y, right? In our x, there's no forces acting on it. So we do v, d, and t, right? We use physics principle 0. In our y, we are accelerating, so we use physics principle number 1 because we are accelerating in the y. Okay. So we know in the x, it moves 16 centimeters, so 0.16 meters. It also said it was moving at a constant velocity, so it enters with a speed in the x, 3 times 10 to the 6 meters per second. Didn't give myself much room there. Right. So we can use v equals d over t equals d over v, and we can figure out our time here, right? It's just going to be our distance, 0.16 meters, and it travels at 3 times 10 to the 6 meters per second. So it's going to be a very tiny time. So we get 5.3 repeated times 10 to the negative 8. 5.3 repeated times 10 to the negative 8 seconds. That's going to be our time, and I just filled those in there. Okay, so we need some more information about the y. So it's like a horizontal projectile, so my initial speed is 0. We don't know our final speed. We're trying to find our distance in the y. That's what we need to know. And we don't have our acceleration, but we have this right there, right? So if I move my m down below, we can find our acceleration. So they give us our electric field in the question, 150 newtons per coulomb. Right, our charge is an electron, so 1.6 times 10 to the negative 19 coulombs. And the mass of my electron, well, I know that, 9.11 times 10 to the negative 31 kilograms. So I plug that in, and I can find my acceleration. 150 times 1.6 times 10 to the negative 19. Let's throw some brackets around there. So we can do it all in one. So we've lessened our calculator, divided by 9.11 times 10 to the negative 31. And we get a huge acceleration, which makes sense because it's really tiny and it's accelerating. So we get 2.63 times 10 to the 13 meters per second squared. And now we have 3 of 5. Now we can use VI, VF, DAT, and we can find the distance. So if we finish this off with D equals VIT plus 1/2 AT squared. Our initial velocity is 0, so we can get rid of that. So to find our distance, it's just going to be 1/2 times our acceleration, 2.63 times 10 to the 13 meters per second squared, in a very small time of 5.3 repeated, times 10 to the negative 8 seconds. Got to square that. And I have those both in my calculator. So if I go 1/2 times my acceleration times my time squared. Don't forget that. Oh man, what did I do? Forgot my times. And I get 3.7 centimeters. Which makes sense, because if I go 16 across, 3.7 down is, and I get the correct answer, and I'm happy with myself. Good work, Mr. Latte. So we got one more question for you. It's a board question. So pause the video, try it yourself, and I'll go through it. So a proton has initial speed in the y direction. Ooh, a little bit weird. It enters a uniform electric field of 200 newtons per coulomb. Find the initial speed of the proton. It's a proton this time. Okay, let's do this. So pause it, try it. Let's do it. So first thing I'm going to do is I'm going to draw a free body diagram for my proton in these plates. So this is my positive plate. This is my negative plate. So when my proton's in between here, my proton's attracted to the side. So it feels an electric force that way, right? So when I do my little chart of x and y, right, in the x, I want to use physics principle number 1 because it's accelerating the x, and I use physics principle 0 in the y. So this is going to be v, d, and t because there's no forces in the y. This is going to be vi, vf, dat. in the x. Ooh, tricky. Okay, what do I know? So I know initially I don't have any velocity in the x. It doesn't start accelerating until it gets between here. It's really confusing doing this. We want to find the initial speed in the y, right? Because it's just moving in the y first. We know that in the y, up and down, it goes 18 centimeters. They give that to us in the question. In the x, it moves 7 centimeters, so 0.07 meters. Sorry, that's... Good. And then, so we just need our acceleration so we can figure it out with that because we can write an F net equation. So F net equals Fe, Ma equals our electric field times our Q. They give us the electric field divided by mass just like we did before. So it's going to be 200 newtons per coulomb. Our charge of our proton 1.6 times 10 to the negative 19 coulombs. But remember, it has a different mass, 1.67 times 10 to the 27 kilograms. So it's got a different mass, so be careful, than the electron, so be careful of that. So let's plug all that stuff in. 200 times 1.6 times 10 to the negative 19. Divided by 1.67 times 10 to the negative 27. And we get our acceleration to be this. So I'll fill that in. Our acceleration is 1.92 times 10 to the 10. So now we have enough information to figure out our time. We use d equals VIT plus 1/2 AT squared, and our initial velocity in the x is 0. So to find our time, we move our 2 up top, our a down below, and square root it, and we can find our time. So it's going to be 2 times 0.07 meters divided by our acceleration, 1.92 times 10 to the 10. And we have to square root it so we can figure out our time. 2 times 0.07 divided by this. Then we square root it. And we get our time to be 2.7 times 10 to the negative 6. Finish it off with V equals D over T. So 0.18 divided by 2.7 times 10 to the negative 6 seconds. And when I do that, I did everything correctly. So 0.18 divided by my time. And I get the speed, which is reasonable. We have 2 sig digs, so 6.7 times 10 to the 1, 2, 3, 4. 6.7 times 10 to the 4 meters per second is my initial speed moving upwards for that. Whew. Okay, lots of homework with this one because there's lots of different things. I'm sorry. Projectile motion style questions, conservation of energy questions, and electron volts questions, charge and current, electric field between parallel plates, and electric force on a test object.